Thank you for being here. Welcome to the World Software Architecture Championship at Nexus. We're trying to do this as as a boxing match to try to compare two heavyweight, the heavyweight champion, which is Microservices on your left, and compare it to the young challenger, Serverless on your right. So tonight's pay-per-view fight that we have is for the best event-driven architecture, and so for us to be able to compare these two frameworks, we need to first set up a standard problem statement that we'll be working on, right? So just to give you some background, what we're going to be doing is we're going to be trying to build a restaurant service which serves pizzas to its customers. Right? And for us to be able to do this, it's a pretty small contained application, which will have three services. You would need a menu service, which has a list of menu items that customers can order. Speaking of, you have a customer service to contain a list of customers and their contact information, their whole life cycle of registration and every other thing that they need to be doing to the customer object. You also have the order service. This is the actual business application where you can place orders and order your pizzas. Each of these services have database tables that they connect to, and they have HTTP traffic that comes into them from the client itself. Right? That's a quick overview of what we are trying to achieve on both applications, so that we can compare the two architectures and try to see what the differences are and what the pros and cons really are. So the first, let's introduce the undefeated, probably the undisputed champion for developing services. It's a superstar in this space, the champion, Microservices, right? So it looks pretty similar to sort of the image that we just saw, but since we are going to be doing this in an event-driven fashion, there are a few more components which will come in. The first one is the event bus, right? Quick overview: the event bus is any messaging solution which we are using to distribute events between different systems. An event is something which has happened in the past and is immutable in state. For example, a customer registering is an event on your system, right? So whenever a customer comes in and registers, you would fire a customer registered event onto the event bus. This event would then propagate across all of your systems, and downstream systems, whoever cares to know, cares about this information, will take a copy of this and act upon it as they see fit. So the customer, so the distribution is taken care of by the event bus. And we usually use a framework, something like Axon, to take care of abstracting out the low-level details of doing the message distribution, the event handling, and all of that. And I'll show you code samples about how that stuff works really quickly. It's not super pertinent to the discussion at hand, but it's really just so we get a common understanding of what the application's like in this space, so that we can compare the two systems, right? So let's look at one of these things, one of these services, and actually blow it up and focus on some of the details of what the inside of this service looks like. So when we actually look at the code and analyze different pieces of it, we will see that there are four, a bunch of different components, but they are of four main types. The four component types include the HTTP controllers, command handlers, event handlers, and aggregates. So let's try going through them really quickly. So HTTP controllers are, we're using Spring here to help us build these things. So you've probably seen annotations like this on your Java code in case you're building a Java Spring-based microservice. So you will have a method which actually handles the post request. In this case, the method is a add menu item. It's a method to handle add menu items. It takes a post request, and the body is a menu item request body structure. It takes the object. It does some basic structural validation on it to make sure that it's structurally appropriate Like there are the mandatory fields are there, and there are no extra fields that you don't expect. You then end up firing in a typical CQRS application. You then end up firing a command. Now let's talk about what CQRS is really quickly and what commands versus events commands really are. So CQRS stands for Command Query Responsibility Segregation. It's a design pattern which is used generally to separate responsibilities of write versus read. So if you look at typical CRUD applications, 3 of the 4 letters there, the create, update, and delete, are write operations, right? You're writing to, you're changing some information. You're either adding it, updating, or deleting it. And read is a separate operation, which does not make any changes. The reason you're separating these two is because in some applications, you have a different profile of load available. One of the places, one of the clients I worked for had a 40:1 read to write ratio, which means for every 40 read requests, they had 1 write request. So from a elasticity and scalability perspective, they needed the read side to scale a lot more than they needed their write side. So you would then start doing optimizations to make sure that the read side works really quickly, because most of their customer use cases, 40:1 in this case, were really read-based, right? Which is, like, when you have these kind of use cases, when you look at the customer profile and you notice that traffic is really different across the two, you generally tend to lean towards a CQRS application. And event-driven if you look at what Greg Young, I believe, says, is whenever you look at CQRS, generally event-driven architecture is not that far off, and soon after follows event sourcing. Now, you don't have to do the 3 together. You can do each one of them separately, but the 3 of them usually come together as a package. So in our case, when we were building this application, the sample actually does all 3 of these. It does event sourcing, event-driven, and CQRS altogether. Coming back, so the command is essentially is a request to change something on the right side. So if you want to either add, update, or delete something, you will fire a command. Commands inherently can be rejected because of business rules. So when you say, I'm about to fire a add menu item command, you're telling the system, the client has asked me to do this. I don't know if I want to do this just yet based on whatever business rules I have, but can you take care of this work? When you fire a command, which is like midway through the sample here, it has to then Axon as a framework then routes this call into a command handler, right? And which is why you have a annotation on top saying add command handler. So whenever a method has the annotation on top, whenever there's an add menu item command fired, it will call this method. And inside this method, you're doing 2 things. You're doing business level validations. If you have rules such as, let's say if an account has $100 in balance, you cannot subtract $200 from it. Right? That just seems like a decent a business rule for most most savings accounts, I guess, right? So those kind of rules are really what you'd validate here. In case something fails, you'd throw an error, which is why you're doing the validation on the top, followed by you fire an event announcing the fact that you've accepted this change. So in this case, what's happened is that you've done some validation, made sure the description is not null. That's the only validation we wanted to do. And then you're saying this looks valid. I can remember that the fact that this happened. So you're firing that event. So you call apply on an event, which again is a CQRS, which again is an Axon implementation, where it takes the event, it publishes it onto the bus, like the example we saw, the animation we saw earlier, and it propagates the message everywhere. So when the message propagates, like Axon is taking care of actually putting it on a bus, and other events, other services, whoever listens to this kind of event automatically gets a callback. So there'll be another part of your code which actually listens to the event. And here the method, if you notice, has a @EventHandler notation, which actually tells Axon to make sure that this event gets called whenever an add menu item event is fired. The reason this bit is important is because this is essentially registering a listener to that specific type of event. Whenever you get the event, you will probably make whatever state change you actually wanted to do. So when the fact that you've said that you want to add a menu item, you're going to save in a items table, you're going to save another entry of an item and make it available. The last thing is aggregates, not really crucial for this conversation, more for the CQRS folks in the room. So I'd quickly gloss over it. But an aggregate, the simplest way to explain an aggregate is probably to say that it is a business object which has state. So when a bunch of events have happened, like in this example, it is a menu item class. If you repeatedly, if you create a menu item and then keep updating it, an instance of this object will contain the latest state of where it is. So if you, in the beginning, let's say you created a menu item for this bottle of water and said that it has like 200 milliliters of water in it. Then you can update the menu item and say, hey, it's actually 500 ml, that's all we support right now. So you can keep doing those updates and the object state will then have the latest state of the object that is available. So this is more for CQRS, so we don't need to deep dive into this. As I said earlier, the code for the entire application is available up on GitHub. If you don't get a snap of it right now, don't worry. It's also at the end of there's one slide which has all of the links in it, and you can just take a snap of that at the end. So let's go back to what the application looked like. We had all of these different components structured in layers. And the important thing to remember here is that we're using Spring to actually make our controllers work, right? Spring takes care of the wiring. As soon as the call comes in, it makes sure that my method gets called. I didn't write the low-level code. I didn't write the servlet, which actually did the parsing and make sure that the right method got called. All of that is abstracted inside Spring. Similarly, event handlers and command, the remaining three things, the command handlers and the event handlers, have a fair bit of complexity to make sure they get called correctly. But we are not really implementing it, right? We have a framework, Axon in this case, take care of all of this, right? So we're using two major frameworks, and we're trying to focus as much as possible into building applications and less into building sort of the lower level code of distribution of messages and calling your methods. So this is what a traditional microservice would look like. You probably built a few of these, irrespective of whether you've done event-driven architectures or not. But let's try to compare this against what a serverless equivalent for this problem statement would look like, right? So we'll move on to the pride of cloud architectures, the evolution of where this journey is taking us, microservices. So the application overall, conceptually, still has the same set of layers. You still have the same components. However, the code which was actually gluing everything in is a bit different. We're not using Spring and Axon anymore. So we're still writing essentially just those methods, and I'll show examples of those. But we're using Express instead of Spring to make sure that the call gets routed to the. For the web layer, for writing controllers, we're using Express, which is a Node.js implementation. For writing event handlers, we're directly implementing Lambdas. For the other two, they are also running inside AWS Lambdas, but we've written some custom code to make sure the wiring exists. Like similar to what Axon does, we had to write some amount of code. All of this will be can be extracted into a framework, and it's something that Vinny and I both are working on doing. Now, if you've noticed, like there is a small difference in the explanation that I gave. For one of them, I chose Java as the language of choice, and the other one we chose Node, and that might strike you as odd. But the real reason why we switched languages halfway through is you can do all of these. Like you can build Lambdas on Java. It works fine. There is nothing wrong with it. The reason why we really switched was around scalability and cost. So Lambdas, for example, if they run quicker than a certain amount, like I believe it's around 100 or 150 ms, AWS will not charge you for the instance. You can say that we were trying to be cheap, but yeah, that's what we were trying to do. We didn't want to pay for the instances as much. Also, we wanted to show you the full capabilities of how fast it can be. So like when we come to the performance numbers and the comparisons, like keep that in mind. Like there is a small amount of time that from a startup perspective, especially from scalability, where not using Java does help us a bit. So the numbers can be misleading. So I will preface that when we talk about performance later in the talk. But for now, we did switch over the language. We did do a full comparison between Java and
and Node.js, and we just preferred the Node.js version. But if you're looking for the Java version, we can talk about that as well. I can try to pull up some samples from history. So let's move into the same layers and what the code looks like. Structurally, you'll see the same set of actions being done. But since we don't have a nice framework like Axon, I did have to cheat in some of these screenshots. And I'm hiding some of the complexity when I took the screenshot. When you go to the repo, the methods will be slightly bigger because we are doing some of the wiring code. Again, you could abstract that out and build a framework out of it inside, which works in JS, but we were not there yet in our project. So the HTTP controller, like I said, still contains the same same declaration telling you what kind of messages you're looking for. In this case, any call which comes into the the service endpoint /menu /item /command /add will come here, and you'll do the same set of things. Command handlers, similarly, as soon as you get a callback for a command being fired, add menu item in this case, you're doing the same validation to make sure that the description is in null, and then you're building a list of events and actually firing them. The event handler is handling the event, and similarly, the aggregate is updating itself to make sure that the current state is managed. Right? A fully functional version of this code is available there. Is available at the repo that showed up at the bottom. It does give you instructions on how to run, what the prerequisites are, and all of those things. So I do recommend you play around with that if you're trying to sort of get into building serverless applications. For any comparison, you also need a bunch of judges, right? Because the results of the comparison really depend on what lens you put on it, or what your requirements really are. And based on the kind of requirements that you have in the projects that you're working on, the results of what we're about to discuss will be a bit different. And of course, it is really hard to take the 200 odd people in the room and go through every one of your use cases. So we try to divide that into 3 main buckets based on personas, right? Some of this is a bit of a generalization, but hopefully all of us would fit into one of the 3 buckets that we've shown. The first individual we have is an enterprise user. General characteristics: this person's looking for stability in the product, a lot of support to make sure that everything works well. Time to market is important, but at the scale generally tends to be months to years in terms of getting a product live. And the main thing to focus on is stability of the product and making sure that there is good amount of support available. The second kind of user is obviously the stark extreme, the startup e-user that you have. And in this case, you have this person's really looking at time to market again, but in a slightly different scale. You're looking at trying to go to market within weeks or months. And the other thing that this kind of user usually looks for is quick feedback. So as soon as they gain insight into their business and they need to change something, they should be able to do it really, really quickly with minimal amount of effort, right? So if the setup cost of your project isn't that high, then this kind of a user generally is happier. Enterprise user, on the other hand, does not mind slightly higher setup costs, but for something which has a lot more support and works longer term. So these are sort of 2 extremes on the spectrum, and you probably expected that these are the personas we'd pick. But having an even number of personas makes it harder to actually mathematically evaluate which one wins, and you need to have an odd number. So the third one that we chose was a persona we call the user, the student. And this one's interesting because what we're trying to do here is that we're defining this persona as someone who is new to distributed systems, has not worked on building event-driven applications on microservices or on serverless, right? So if it's your first time trying to do this, or you've never built a large microservices-based project either, you're probably closer to being in this bucket, right? You have prior programming experience, you understand how programming works. It's just that this is a new space for you. Right? So a while back, I used to be a desktop dev, so I didn't really do services as much, like large-scale distributed services. So I was in this bucket, a couple of years ago. So I guess couple is a
simplification, but never mind. Okay, so now that we've sort of set up the stage, we've talked about, we have talked about, what the problem statement is, what the two individual applications look like. We have also talked about, really quickly what the personas are and how we're actually judging this comparison. Let's talk about the actual differences between the framework, right? Like frameworks and what it means to you, the potential devs on the team who are trying to build this application, maintain it, et cetera, right? And for this, what we decided to do was we decided to pick up a bunch of cross-functional requirements and try to score the frameworks across these different cross-functionals. So the first one well, some of them are cross-functional, some of them are functional, but the first bit that we wanted to pick was deployment, right? Like how easy is it to try to deploy your code, right? And this tends to lead towards time to market and ease of setup of the project, et cetera, right? So let's look at microservices. So for a microservices application, which is built out of Spring Boot, as the example we were taking of, it helps you build a microservice. In case you've not used Spring Boot before, I guess a quick introduction would be that it is a bunch of features which will help you build services really quickly, microservices really quickly, and provide the health, the monitoring, and observability that microservices really need. Without you having to repeatedly set that up. It's a really nice framework which will accelerate development of microservices, right? But like when you have one of these and you build your entire service out, what you're expecting, the artifact that you expect is a jar file, right? You could also take a war file if you want to. But this jar file is ready to run. You could just Java jar name to it and it'll start up. It'll whatever port you've configured it on, it'll be enabled and it'll be ready to invoke. So you take this artifact and you're ready to run it, but there are a few things that you have to prepare before you can actually run it, right? And again, like the rest of this conversation now is going to depend really on which of the buckets you're in. If you're working in a space where you're deploying on bare metal servers, you have to make sure that first a server is available, which has capacity. If you're doing VMs, it's the same thing. If you're doing, if you're deploying on AWS, then make sure you have the permissions and everything else. So I won't really go into some of these details, but let's assume that you were trying to do this as on something like OpenStack, which requires you to provision VMs every single time using something like Ansible or Chef, right? Which might hopefully be a sort of application space that a lot of you have either worked on or are currently working on. So if you have such a space that you're trying to deploy to, you first need to make sure that you have capacity. Let's say that's checked off. You get a new VM. You probably want to put an operating system on it just to make sure that everything's working. You have an image already ready. Just slap it on and boot it up. That's step one. If the image is not close to where you want it to be, you might sometimes also have to install Java on it, because you need JVM to be able to execute these things. So you take something like Java and put it in there as well. At certain enterprises we've worked at, like they don't want you to deploy on Spring Boot directly because it has an embedded container, and some of the deployment support that they have doesn't really work with the embedded container. So they explicitly ask you to install something like TCAT, something they've bought support for and have a lot of scripting and monitoring pre-configured. So in this case, you can take the jar file and actually put it onto TCAT. But before you do that, you actually need TCAT installed on your server, right? So whatever the prerequisites are, you have to install all of these, and you have to make sure that the server is provisioned correctly. Once you've provisioned, the actual deployment process is pretty easy. Like put the jar onto the machine and run the jar. If it's Spring Boot, then Java jar run. Otherwise, whatever your container needs, do those steps, and the application comes up. So the actual deployment process is pretty small, but the setup process, the provision process, is slightly more expensive when you're doing microservices projects. So most of the places I've been to, we'd spend some amount of time in the first few iterations setting up this pipeline, optimizing all of this, and making sure we can deliver really quickly. So you go slow in the beginning, and then you pick up speed. Once all of this is automated really well, it goes a lot quicker. but your mileage may vary based on the stack that you use, right? So if you're using OpenShift or something else, it's a lot quicker because you're just deploying Docker images. Let's move over to serverless, right? And once you write your code and you check it into version control, the next step is to obviously test all of it and build an artifact. Well, the artifact in this case happens to be if it's a Node.js app, which is the example we took, when you build the app or package it, it will become a zip file with all of the code. And the other bit of the artifact is also producing a bunch of AWS configuration. This configuration includes you telling AWS under which event do you call which Lambda. Now, here the word event means something slightly different. So when you say there is a event which happened, there's a bunch of providers that Amazon already has set up. Things like HTTP requests, right? A pretty standard thing. It'll give you a URL. As soon as you hit that URL, if a client hits that URL, your Lambda will get called. Another example is if a message makes its way into the bus and the message has a certain type, it will call your Lambda. And there are a bunch of other things. You can detect changes on S3, and I think there's probably around 8 or 10 different types of other connectors that Amazon just comes out of the box with, right? And these will cover a lot of the use cases that you want to do, like that you need to set up on, in a event-driven application. So we're going to be using all of the available event types that the serverless provider already gives us, and work off of that. So like you're generating configuration to tell the serverless provider, AWS, for example, what Lambdas to call and when to call them, right? The pieces of code that you had seen earlier, there needs to be some amount of configuration to be able to call all of those. And after that, what you have to do is you have to upload the configuration. And the configuration also tells where the zip file is. Put the zip file on S3, and Amazon runs its magic, and your service is then available. Right? This is the deployment process for an app which was built in JS and packaged after that, and then deployed to Lambdas. So this is one way to deploy it, and it does sound tedious and painful, right? And I wouldn't be standing here and explaining all of this if there wasn't a better way to do this. So there is a open source framework which has been developed recently, I think over the past couple of years. It's called Serverless, like quite obviously named. I forget what the TLD is, but it's, I think, might be serverless.org or com, one of the two. Just look up Serverless framework, and this is where like this talk might get a bit more confusing. So let's get our nomenclature straight. When I say serverless provider, it means a provider like AWS or Azure, someone who gives the capability for me to deploy Lambdas. When I say serverless framework, it means the framework which actually helps me abstract out my code, deploy my code easily, and test it, right? It's a binary which is installed on your local machines. It's a binary which is also available on, you probably want to put it on your build machines if you have a CD pipeline as well. So the nice thing about this framework is that it is abstracting out different vendors. So you don't really have vendor lock-in anymore, because all of the configuration I talked about how you configure the HTTP event to actually make it to your Lambda, is really specific to AWS if you're building for AWS. But if your organization wants to switch to another provider, well, you'd have to write the configuration again. Well, serverless tries to make it a lot easier. You're spending a hell of a lot less time to actually deploy your code. You're writing a few lines of code, and it generates most of the things out of a template. Second, those things are agnostic, so you can change a few words on your configuration, and it will actually switch over providers as well. And third, it also provides you like offline testing tools to make it quicker and easier for you to develop offline. So if you're sitting on a flight and you want to experiment with stuff, assuming that you've downloaded all the binaries that you need first, you can do full development locally, like including like using backend as a service for things like DynamoDB or SNS. So all of that is provided as a backend, as an offline service as well. So you can go into flight mode and still write code, which is a pretty useful thing considering half of the room I can see has laptops here and are probably taking notes. I'm guessing that's a use case that will help you guys as well. So if you look at it this way, like because of frameworks like serverless, it becomes easier and quicker for you to deploy code when you're deploying it on serverless than than microservices if you don't have cloud native applications. Second thing we want to try comparing these services on is availability, which essentially means when you deploy a version of your application and you have customers giving you live traffic, you obviously aren't done the first time you release code, right? Like you probably want to make feature changes or bug fixes, and you want to continuously keep improving your application, right? So you build a version 2 of your application, and some of this is going to sound obvious. There are tons of strategies to make sure that you deploy newer code without affecting the existing application. One of them is blue-green. So if you're doing blue-green, what you're doing is you're setting up a second server, you're provisioning it, making it all ready, deploying the code on there, while all of the traffic which was already coming in keeps through a load balancer keeps going to version 1 of your application, right? So once the server is all provisioned and you've deployed all of the code, you can start smoke testing it in the background. It's not really live. Customers are not affected. You can probably hit the application, make sure the health is up, that the services are doing what you think they should be doing. And once you're comfortable to release software, you hit the button, and there's an instantaneous switch over from on the load balancer from version 1 to version 2. Your users don't know anything happened, like anything significantly changed, assuming that the application works fine. And once you verify that there are no errors and your monitoring says everything's fine and you're comfortable, you can tear down version 1, right? So that's how you deploy, like on a blue-green strategy, you would deploy, you do a safe deployment. Well, the blue-green deployment actually requires you to take the effort. You have to implement this in your organization and make sure you have the capability to do these kind of things. For someone like me who has to periodically work in different projects in different organizations, that means repeatedly going to different clients and implementing something quite similar. So if you're a consultant or work in the service industry in general, you're probably looking at going from client to client and implementing one of the zero downtime deployment strategies. And that's a fair bit of work that you're reinvesting in every single time. But since you're moving, if you're moving towards the serverless land, it's more of a managed service. It's things that you have to worry less about, so you can focus more on your development. That's the sort of promise we that we were given. So let's actually evaluate how that works. If you have a version of the app available, which actually has live traffic right now, and you develop a second one, it implements internally the rolling deployment for you. So it spins up a new instance, it deploys all of the code and switches traffic as soon as you hit serverless deploy. That is something that AWS does internally, and we didn't really have to write code. So our deployment strategy also becomes simpler in the application when you do something like this. So we recognize that there is some amount of control, for lack of a better term, that you might be giving up because if you want to choose a different deployment style, you don't have that anymore. But that's a trade-off that you're probably willing to make for velocity. Again, it depends on what levers matter more to you. If you're tuned into having more velocity and deploying really quickly, then probably serverless is better. If you want more control and stability, you might want to go the other way. Right? Talk about something a lot more interesting: scalability. To me, this was a pretty important factor in trying to choose between these and when I would implement these individual patterns. So if you're working in a large organization which manages their own hardware, which I'm guessing some of you in the room are working in a similar space, I call it the pay first, scale later approach. Right? And what this really means is that when you start off a project, you first have to estimate the amount of traffic that you think you will have. You will make sure that the amount of, you put money on the table if required and buy more hardware. Once the hardware is available, you spin it up, you deploy your service on top of it, and customers start using your service. Right? You make sure that there's monitoring on top of this to ensure that you're not overutilizing your resources and you're not leading to degradation of customer experience. Now, if you're really successful, let's say you're a shopping website and it's Black Friday, you know what's going to happen, right? most of us will be on shopping websites refreshing really, really quickly, trying to get the best deal that we can. The number of users suddenly went up quite significantly. And when this happens, your alerts go off because you can't scale quick enough. So you're probably losing customers. Of course, you can avoid it. Most organizations avoid this by making sure that around the holiday period when you have more traffic, they fix this problem by putting more money on the table, making sure the hardware is available ahead of time because there's a certain usage pattern and it's more predictable, and they add more servers in place, right? Of course, you guys have already heard of this. This is nothing new. This is not having elastic scalability is what you're seeing here. Of course, if you work in an organization which has elastic scalability, congratulations. This is not the problem you have, but there is still something in it for you. We'll talk about that soon. If you are working on the other spectrum, and let's say your applications are deployed on a host like AWS, which does have elastic scalability, you're still taking time to actually configure elastic scalability, right? You're putting in limits into how quickly you want to scale, when do you want to scale, is it at 60% CPU or or higher or 80%, and you're setting up all of those metrics and you're trying to tune it perfectly to make sure that as your traffic spikes up, you scale up and you scale down again at the right amounts of time. You do it too quickly, you're paying too much. You don't do it quickly enough, you're probably losing customers. So that's the trade-off you're trying to make, but that's something that you as individuals on the team are really trying to configure well. If you move over to the serverless bit, it is a lot simpler. When you deploy your code and you have traffic on it, we didn't tell AWS how many instances of the app we want, or it's not even app, it's how many instances of the Lambda we want. When there is a burst of traffic, it's not a problem that we necessarily need to solve. It is something that, again, the serverless provider provides scalability at the method level. The important thing to note here is that you are scaling not at a service level, you are scaling at the Lambda level, which means that if one endpoint sees more traffic than any other, you don't spin up entire services, which are a collection of these endpoints and business functionalities. You don't spin up a new menu service. You just spin up more instances of the add menu item service. There are a couple of advantages of these. The Lambdas are significantly smaller. Being significantly smaller means they start up significantly quicker, right? A typical Spring Boot application, which has a decent amount of functionality baked in, would probably take 30 to 45 seconds to start up, right? Because it has to establish connectivity to the database, to the queue, make sure everything works. It's probably 30 seconds before it services traffic. So you can only scale that fast when your service starts at 30 seconds. And 30 seconds is by no means a bad number. It's pretty good. But compare that to a Lambda, which is just a function. You're just starting that, the virtual machine, for lack of a better term, which this thing runs inside. It takes less than a few milliseconds. So the rate at which you can scale up is significantly higher. And again, you're not configuring any of it, so it's lesser development effort for you to build these in, and you're scaling out a lot quicker as well. The thing that you're monitoring in these cases, much like most other public cloud-friendly solutions, is that you're monitoring the cost, not the you're monitoring the cost, and the reason you're doing that is because you are scaling first and paying later, right? So you probably want to put a cap on it just to make sure you don't get like $100,000 on your account if it's a personal account that you don't want to take that tab, or whatever is an appropriate amount for your organization. Right? So the incentives are slightly different, and the way you configure it is slightly different. But there's significantly lesser work in trying to scale your application and tune the scalability because of the speed at which you can do it, and the amount and the configuration that you simply have to put in. Let's move on to round 4, extensibility, which is the ability to add a new service or new functionality in. Right? So we started our service with we started our application with 3 services. If we had to add a 4th one, and just add more functionality to it, let's look at the number of boxes we'd have to check before our service can go live, right? Which in turn determines the amount of effort it would take to go live with an app. So you would obviously write the application code. There's no going away from this. You have to do the business logic work. You have to build a pipeline. And you already done the assumptions. You've already done the investments we talked about, right? You've invested in doing the pipeline. You just have to add some configuration in there. If you've configured it correctly, it's probably a few lines of code to just spin up a new pipeline after that. You have to make sure that the right instance is provisioned. You do the deployment configuration to make sure that you're using the right strategy for deploying it, and you're just hooking up to the right amount of monitoring and making sure everything works correctly, right? And that's when you have a service live in production. Now, if I'm trying to do the same thing on serverless, you'll have a bunch of lambdas which are using for its database. It's not really using something that we've spun up. It's in our case we use DynamoDB, which is an offering, a backend as a service that is provided by AWS. We are also using SNS, which is like a message distribution service that is provided, kind of like MQs. And so when we wanted to add another Lambda, it was simply the work we had to do included adding a function, the function with the actual business logic, adding configuration to make sure that it gets tied in together. The build pipeline is basically running SLS deploy again. That's the only command we had to do. There is no provisioning because we are not managing the services. The deployment configuration, as I said, was a few lines of code that we just had to duplicate. If it's a new HTTP endpoint, it's the same set as the last one, so just duplicate it, change the endpoint code, and change the method name, and the entire thing is configured end to end. Monitoring gets set up automatically when you push a Lambda in. So if you're using something like CloudWatch on AWS, it will automatically know that there's a new Lambda. It will show up on your dashboard as soon as you do that. So the amount of effort we've taken to add a new service, like if you've done it right on microservices, it's not a lot of effort because you made the investment in the early days of your project. You've actually automated all of your deployments and everything else. But it is still quicker, slightly in a comparative sense. You are still saving a bit of time even on the serverless bit, right? But it's closer to being a tie than anything else. Assuming you made the investment in building your pipelines and everything else right the first time, and you built it for extensibility, you won't have much of a problem. Let's come to the one of the most important things when it comes to microservices, right? How are we actually monitoring the services? How do we know that our functionality actually works, right? So anyone who's built microservices knows that you have to be able to observe your services and understand what goes on in the inside to know that your application is working correctly. And this is where something like microservices really shines. It's because it's a architectural style which has existed for a long time. The ecosystem is really, really rich, right? So before we go into the ecosystem, let's look at what our set of services really looks like. Like we have a bunch of servers which run our application, but we also have a database, we have a queue, and we have an API gateway just to route our traffic. Now, in the microservices ecosystem, you probably want to monitor not just your services, but also the entire value chain to make sure that everything on the entire stream works correctly, right? So you'd have monitoring on the apps as well as the apps. The health endpoint on the applications itself will contain information about whether the database is connectable, whether it's up. Same with the queue and everything else. If you used Spring Boot before, or you went through the Spring Boot workshop yesterday, you've probably seen examples of some of these things as well, right? So once you do all of these, you're probably then setting up a bunch of tools in your organization. If you're doing this for the first time, making sure the ecosystem for monitoring exists. If this is on AWS, you'd probably use CloudWatch, as I was mentioning earlier. For logs, you're going to make sure that you have Logstash so that it aggregates logs from all of these services. You probably have multiple instances of the same app. So like for a menu service, let's say you had 3 instances, you have to make sure that logs from all 3 of these instances make it to the same place, because it's a nightmare to have VI windows in multiple places, right? Like thankfully with tools like Elk showing up,
I'm hoping gone are the days where we have to log into like 6 different VI terminals on a development or a production box to look at logs. And there are nicer tools which help us do that a lot quicker, right? So Logstash is one of them. Kibana is the UI bit of Elk, which takes care of dashboarding, takes care of aggregation, and if you also put Elasticsearch in the backend, if you push the logs into Elasticsearch, you can also make them searchable, right? So the Elk stack is pretty popular. Hopefully some of you are already using it or trying to move towards it if you're building microservices. You probably also have apps like New Relic and App Dynamics. Both of these are paid apps, and they're generally used to monitor individual instances and make sure that the CPU usage, the RAM is correct. And you're also trying to make sure if your business flows actually work. Because the application spreads, because a business flow might spread across multiple applications, right? For the user, it's just a couple of clicks for something to happen. But from your perspective, you're calling 3 different services to make that happen, right? From a services perspective, yes, logs tell you what happens. But if you want to look at the whole transaction from the user's perspective and make sure that all the services did what they wanted to, you probably want an aggregated view of whether everything worked or not, right? And tools like New Relic and App Dynamics are really good at allowing you that capability and making sure that you can make sure that the end user is actually getting the value that they need. Also, if you're spinning up services yourself, either because you're deploying on bare metal or because you're using VMs, you probably want apps like Nagios and or Zabbix. Like they do slightly lower level monitoring to make sure that the individual apps work. The actual instances themselves are up, right? So there are a lot of tools here, and you've probably used a lot of these to make sure your monitoring suite works. But if you're the first person in your organization who's trying to set these up, you really have to spend time to set these up the first time. But if they're already available, the ecosystem's really rich, and there is a lot of power behind these. If you compare this with serverless and you're trying to understand how you can do monitoring here, well, first off, the queues and the databases, we're not really worried about as much because they are services which are provided by the cloud provider themselves, right? So we're going to ignore the connectivity because it's on, all of that is a managed service. But we're using tools like CloudWatch as our sole source to make sure that our application works. There are dashboards in there which actually give you this information. The other bit is you probably also want to monitor the cost. So you can use the billing dashboard, which is available inside Amazon, to do this information. Of course, if you don't like going through a bunch of menus and trying to figure out where Amazon's put what inside which sub-menu, the UI can be a bit daunting if you're doing this for the first time. There are tools which aggregate all of this information into one dashboard and make it a lot easier, especially from an ops perspective. From an ops perspective, you probably want graphs to be able to understand what your traffic profile looks like. So there are tools like Dashboard, which are available, which will do exactly this. So I realize that the screenshot is not big enough for you to see it, but like there are some graphs in there which actually take the amount of requests that you have per second and a bunch of other metrics that your ops team would really appreciate, right? And at the bottom, if you notice, there is like a small red box. That's because we simulated an error, and it shows you those as well, and you can drill down into those and actually look at what went wrong. So it gives you more diagnostic information as well. They also have a similar billing dashboard, so there's another page right there. So in 2 simple pages, you can get most of the information that you would look for if you're deploying an application. So because these are managed, these are services which are on a public cloud, like there are the monitoring solutions are easier to set up. But the downside is, personally, like the ecosystem's not as rich yet. And that's not really the fault of the framework just yet. It's because you're on the early end of adoption, which is, I'm guessing, the reason why most of you are in the room right now, right? It's pretty early on, and the tool chain is not as mature as the microservices tool set is. So if you're in this space, your providers, the tools that the provider has given you probably give you the most information. But if you want some abstraction, a better dashboard, some of them are available, but they might not. They are nowhere close to something like an App Dynamics or a New Relic and the kind of power and visualization they give you, right? But it's only a matter of time till the ecosystem actually gets there. Okay, let's talk about performance, the thing that I sort of alluded to earlier. And let's get like the comparison numbers first, like the benchmarks in first. Like how are we actually testing it? It's not a ridiculous amount of load that we're taking right now, but you could change the numbers as you want. But the numbers I'm going to be showing are for 10 requests, concurrent requests a second, 1,000 requests overall. There is a warm-up request, which just makes a get call, which just returns data from the database. And then there's the actual benchmark, which does the 10 requests a second and 1,000 requests overall. For this, we are using Apache Bench, the tool AB on the screen, if you notice it, to actually run the test. Right. The reason why we had to have the warm-up test is because we had deployed this code onto Heroku, and Heroku optimizes for cost, so it will shut down your dynos when you're not using them, which is great because you're saving a lot of money when you're experimenting with stuff. But if your dynos are asleep, it's probably going to take like 30 to 50 seconds before it comes up. As I said, 30-second time startup time for your application. So if it takes around 30 or 48 seconds, the test is not going to look that good. So we did a warm-up, we made sure that everything was started up, and then we ran the entire test. And the results look like this. The number that you really want to note is up there. It's 84 milliseconds per request, if the contrast is not good enough for the folks in the back to see it. The application took roughly 84 milliseconds. There are a few caveats, like I said earlier. For example, we're not even using a database. We're using an in-memory database for the Java application because we couldn't find a managed database on which connected to Heroku. So we're just using H2, which writes to disk locally. So what that means is that you're probably saving 10 to 15 milliseconds on the actual write to the database every single time. The 10 to 15 milliseconds comes from experience because I spent a couple of years doing performance testing on a really similar stack, actually an identical stack. So I was part of the engineering team, so this is the kind of stuff that we used to do. And this, again, is just a post request to make one change. Generally, business flows involve doing multiple things where you post 2 or 3 things, and then you probably also get the result at the end so that the UI actually works. So from a business transaction perspective, including the propagation time for the events and all of that added together, it is anywhere between 150 to 350 milliseconds on an average for a business transaction to work. Right? We didn't simulate the test here because the command isn't a one-liner. It is the test tool then becomes a lot more complex, and I can't show that up on screen. But if you're interested in how to properly performance test and benchmark your application when you have a distributed event-driven application, we can talk about that offline. It's something I'm really passionate about. So the simple test, let's switch over to Lambdas just to see scalability in play and how quickly it can respond. And this is where the commands are roughly the same, and we're sending the exact same request. The payload is identical as well, and the response is identical as well. So at least in terms of the network traffic and the things that we are calling, everything's identical, right? And the result is roughly a fifth the size. So you've gone from roughly 80 to 90 milliseconds to around 20 milliseconds when you're running a Lambda. And the difference really is because when you start peppering it with a bunch of requests, your application takes a lot longer to scale out. Whereas the serverless application, because it's just a Lambda and you're calling the Lambda repeatedly, it scales up the Lambda really quickly. Your Java application, because it's deployed on a VM which has enough CPU and has a decent amount of RAM, you will notice that it takes a lot longer for you to hit the CPU limit and then for you to spin off more instances. So when we did the test, we noticed that we ran all of this into on one instance, and we never needed to scale out. Whereas for Lambdas, we spun up multiple instances. However, the average time for one of these requests was 20 milliseconds, so we weren't even paying for it. So all things considered, we are spending a significantly lesser amount of time actually running the code, lesser time actually paying for it as well, right? And with that, we come to sort of the conclusion, right?
And the result is a bit different based on the persona that you subscribe closest to, right? So if you're an enterprise user, because you're looking for more stability and a richer ecosystem and a lot of support, when you compare the two frameworks, you're probably going to go for a microservices style architecture, right? It's really set. You've used it for years. You know there are no surprises because it's been around for a while and you have a lot of experience. Hiring's probably a lot easier as well for devs in that space. If you're running a startup like shop where you want quick, you really need high velocity and need to deliver quicker, but you don't mind taking a few risks. You would probably go the other way. You would make sure that you could pick up Lambda if you're willing to take the risk and actually take the effort of going through some of the documentation. The startup cost isn't significant in terms of learning and actually getting into it, but that's something that you can do quite easily. The last kind of persona is really the student, and this use case is important because it's when as we said, it's when the user does not know about distributed systems and is trying to get in. When you're building a microservices application, you have to have the big picture in your head. You have to understand the fact that you have multiple services. They connect through an event bus, so I need something like an ActiveMQ running on my machine when I'm trying to play with it locally. The connectivity, you have to learn how to set up the connectivity for the MQ. You have to know how the databases connect. And every other piece, every other dependency has to be set up right. And that's something that you should know how to do, right? So if you're new, that's a bit of effort that you have to take. If you're doing this on the Lambda side, like you have to write a few lines of code to do the connectivity to the databases, but you're not spending a lot of time in configuring it, in starting it up. Because all of those are managed services, when you deploy and when you deploy locally, you'll know, if I was a student, I'd probably go closer towards learning Lambdas first. It's also a framework that in the long run will, like as someone who's trying to pick this up, is also beneficial for you because you're looking at you're really looking at what framework you think will benefit you the most in the long run, right? And if you look at the industry trend, we've over the past 20 odd years, we've gone from building web applications and just deploying them on Snowflake servers to automating all of that and trying to spend lesser time in doing delivery of the software, but more time in building the application code, more time in delivering business value. And if you extrapolate this out, it's probably going to go more towards just trying to focus on business logic and delivering, again, business value to your clients than actually spending on infrastructure, tuning it, and all of these. So, like, again, going back to experience, like I've spent a significant time trying to performance tune, and make sure that the platform that we built on the microservices side scales. And that's really a role that, in the larger scheme of things, like you would want to have less of, and you'd want more of your folks working on delivering like end client value. So if you think the same way, like the extrapolation of this would probably be that we are trying, as an industry, we are trying to go closer and closer towards my serverless style of coding because you're focusing on the business value aspect, right? So if I was a dev working on these things, I'd say that's the architecture I'd double down on and make sure I learn first. Right? And so with that, on a split decision vote, a fight which is closer than most people would expect, you'd have, like, I'd probably choose serverless if I'm any of the two users on the on the right hand side. If I'm a enterprise user, I'd still go for microservices, right? Thank you, and as promised, slides, code, Twitter handle up on screen, feedback welcome there, as well as we have some time, so I can also take questions if you have any.